All right, so we're in 8.3 today. This is the last section in chapter 8 that we're going to look at, where we're still looking at applications of integration. There are two more sections in chapter 8, which deal with additional applications, but we're not covering those because typically if you're going to need those, you'll end up taking a class where those are taught anyways. So we're just going to get through section 8.3, and then we're going to be all done with chapter 8. In section 8.3, we're dealing with applications to physics and engineering, and we're really looking at just two specific applications for the most part. The first of those is what we call hydrostatic force and pressure. So to kind of motivate this, imagine that we have some fluid. It can be water or it can be something else, and it has some density, which we can give by this Greek letter rho. And in metric units, that would be measured in kilograms per meters cubed. So that's the density of this fluid, whatever it happens to be. We're using rho for that. Now, suppose that we take a horizontally oriented plate. It can be like a metal plate or a plastic plate, just some kind of thin surface that we're using or that we're thinking of as a plate. And let's suppose that it has an area of capital A units. So again, if we're talking about metric, that would be square meters. And then let's suppose that it's submerged d meters below the surface of that fluid. What we're looking at here is the force due to the fluid pushing down on that plate. We call that hydrostatic force. Hydro means water, but we're using it in general for just any fluid here. Now, you know from just kind of common knowledge, I guess, that if you say, dive under the surface of the ocean, the further down you go, the more pressure you feel, the more pressure is exerted on you. And the reason for that is because there is more water above you, essentially weighing down on you because of gravity. So we want to kind of quantify that for this scenario here. So here's how we imagine this. Imagine that this plate A, again, it's like horizontally oriented, d meters below the surface of this fluid. You can imagine the fluid as sort of a column of fluid directly above A. So if you were to I'm not going to actually draw this, but imagine from, all around the edges of A, we draw this column of water. Then that column is exactly the part of this fluid that's directly pushing down on that plate A. So if we could determine the force due to gravity of that column of water pushing down on our plate A, that would give us that force that we're looking for. Okay, so how do we find that? Well, let's start by finding the volume of that column of water. Because that column is essentially like kind of like a cylinder or like a prism. We have a basic volume formula that we could use to find it. It's just the area of the base of that column, which would be this plate here, so that capital A, times the height of that column, which is what D represents, because that's the depth below the surface. So the volume of that column of water, V, is equal to AD. Now, if we want to convert that volume to a mass, that's where we need density. So remember, mass is equal to the density of our fluid times the volume of that fluid. So here, mass, little m, is equal to rho, our density, times our volume. And then using our result here, that's the same thing as rho AD. So this represents the mass of that water pushing down on the plate. Finally, what we're after is force, and then we're going to go a step further after that and find pressure. The force exerted on that plate from Newton's second law remember that's F equals ma. Well, in this case, A, or acceleration, is the acceleration due to gravity, little g. So the force of our fluid pushing down on that plate A is mass times the acceleration due to gravity, or mg, which just takes our previous result and multiplies by a g. Now we have rho g AD. Okay? So that is the force of that fluid. How do you go from force to pressure? Well, pressure is a measure of force per unit area. So in other words, how much of that force is concentrated on 1 square meter of this plate as opposed to the entire plate. Okay, so that's really just taking our force and dividing it by the total area of that plate, which, if you notice, using our results for force here, dividing by A is just going to cancel those A's out. So the pressure, which we call hydrostatic pressure, is rho g d. Okay, now a little discussion on units of measure here. So the SI units, or metric units for pressure, would be, if you think of this as force per unit area, would be newtons per square meter, because those are the corresponding units for force and area in metric. That unit, newtons per square meter, is what we call a Pascal. 1 Pascal. Okay? Here's the abbreviation for that, PA. Now, in applications like this, a Pascal is a pretty small unit of measure. And to kind of compensate for that, it's a little bit more common to measure things in kilopascals instead of just pascals. That's 1,000 pascals. The notation for that is K, capital P, A, like that. And it's 1,000 pascals. If we're doing the same sort of computations, but in imperial units, so like the U.S. customary units, then if you remember from like our section where we computed work back in chapter 6, we consider weight instead of mass, and weight is already a force. So rather than pressure being our density times acceleration due to gravity, which, remember, this our density times gravity times the distance below the surface, we just use this. P is equal to sigma d, where sigma represents what we call weight density. And basically the interpretation of that is, again, remember, we were thinking about pressure as basically the force due to gravity on a unit of area on this plate here, so 1 square meter. Now we're just thinking of that in terms of weight per unit area. So that's what this represents. It's weight per unit area, and we call that weight density. Now, like we said, you can do these sorts of problems where you submerge this plate under any type of fluid, but more often than not, in the problems that we see in this section, the fluid is going to be water. And the reason for that is because we know what the densities for water are in these various different units of measure. So in metric units, the density of water is 1,000 kilograms per cubic meter. And in imperial units, where we're talking about weight instead of mass, it's 62.5 pounds per cubic foot. So in the metric case, this is what we would be thinking of as that rho that's showing up, and this is what we would be thinking of as that weight density. Okay, 1 second. Sorry about that. My kids are being really loud, so I have to close my door. All right, so this is specifically dealing with a horizontal plate, like relative to the surface of the fluid that we're submerging it in. So it's parallel to that surface. But in practice, we want to be working with kind of more general situations. So what if instead we wanted to find the hydrostatic force acting on a plate that's not horizontally oriented, but maybe vertically oriented? To do that, we have to use a principle from fluid dynamics, which is experimentally verified, and it says that the pressure acting on a point submerged in a fluid is the same in all directions. I think the example your book uses to illustrate this is like a diver. So if you're a scuba diver and you go under the surface of the water, the pressure that you feel on your face mask, which is acting kind of like horizontally towards you, is the same pressure that you would feel on the top of your head, which is acting vertically downwards, if your body is oriented straight up and down. So that's an important concept here, because it's easy to look at this and see that the force is basically due to gravity. So we imagine that force is only acting downward, but at any given point, the force acting on that point is the same force in all directions. So that is going to help us extrapolate some of this stuff to the case where we have a vertically oriented wall or plate or whatever. Okay, so let's work with that. The idea here is we're going to take a vertically oriented plate. We're going to basically slice it up into small rectangular horizontal strips. And those rectangles are really approximating rectangles because the shape itself may not be a stack of rectangles, you know. And then we're going to approximate the hydrostatic force on each one of those little horizontal slices, simply because rectangles are the easiest geometric shape to work with when it comes to something like this. And we're going to use those as an approximation. We're going to sum them up, take a limit, which is going to end up giving us a definite integral. Okay? So rather than give you a result in a big red box here that says, here is how you find hydrostatic force, we're going to just jump into an example or two and, just see what it looks like. So in this case, we have a vertical triangular plate. It's submerged in water, and we want to find the hydrostatic force acting on one side of the plate. So again, it's vertically oriented instead of horizontally oriented like we saw at the top of the previous page. However, at any given point on this plate, the force acting on that point is the same in all directions. So when we think of the force acting on like one side of this plate, we're imagining that force kind of going this direction, right? But at any given point, the force being applied in this direction, according to that principle we just talked about, is the same as the force acting downward on that point. So what that means is that we can apply all of the stuff that we did on the previous page where we were specifically looking at downward force and apply that to this force applying that's acting on one side of this, one face of this triangle. Okay, so here's what we want to do. Just like when we were doing those work problems back in chapter 6, these are going to feel a lot like those work problems. We want to introduce a coordinate system. So I'm going to redraw that triangle, maybe a little bit bigger. It's my printer making all that noise. And then I'm going to put the surface of the water like right here. Okay. Now, these problems can be approached typically in more than one way, depending on how you're choosing your coordinate system. So for me, I'm going to want to choose my coordinate system as an axis that starts at the bottom of that triangle. So I'm going to call that 0. And I'm going to think of up as the positive direction. Okay. Now what I want to do is label some relevant values. So according to this, I have a triangle that's 6 feet here and 5 feet on either of these sides. That makes that an isosceles triangle. I know that it's 3 feet below the surface of the water, but I don't have like the height of that triangle, which I would need to know to determine some of the values that I want to put on my coordinate system here. So here's what I'm going to do. I'm going to sketch that altitude or height of that triangle. And then I'm going to label a couple of things. So first of all, this is an isosceles triangle, which means that this altitude bisects that side right there, that base. So if the base of the entire triangle is 6, then this must be 3 right there. This is a right triangle as well. I also know that this side right here is 5. And what I can do is use the Pythagorean theorem to find this one missing side of this right triangle. So if you apply the Pythagorean theorem, you'll end up getting 4. You may also recognize this as what's called a Pythagorean triple if you've ever studied those. Those are sets of 3 integers that satisfy the Pythagorean theorem, and 3, 4, 5 is a very common one that you may have memorized. So if you see a right triangle with a hypotenuse of 5 and 3 as one of its bases, if you know your Pythagorean triples, you can say that that's 4 without having to do any real work. But if you don't know that, just apply the Pythagorean theorem. Okay, so what does that tell me? That tells me that from the bottom to the top of this inverted triangle, we're going from 0 to 4. And then according to my image up here, there's 3 more feet that I have to move to get from the top of my inverted triangle to the surface of my water, which would take me up here to 7, 4 plus 3, okay? Now, what I want to do is look at my triangle, and I want to just kind of pick some, or think about this interval from 0 to 4, which kind of bounds that triangle. And I want to imagine cutting it up into a whole bunch of little sub-intervals. And then on each one of those sub-intervals, I want to construct a little rectangle like this. So this is hopefully reminding you of those work problems we did in chapter 6, because it's very, very similar the way that we approach these. Okay, now suppose that where this rectangle intersects the sides of my triangle, let's suppose that that corresponds to some value, say xi star. I use x's, but you're going to see in your textbook and other sources, a lot of times they use y instead of x, just because this is a vertical axis. But because there's only one axis that we're using for this problem, you kind of don't really need to worry about what you're labeling it as, just as long as you're consistent with that label everywhere in the problem. That's really the most important thing. So I have this xi star here. It's kind of telling me the location of that rectangle relative to my axis here. What I want to do is find the area of that rectangle, and then I can use the work on my previous page, on the first page of these notes, to figure out what the pressure and the force acting on that rectangle is. So let's start with the area. How do we find the area of this rectangle? Well, I'm going to think of the width of all of my sub-intervals here as delta x, which is what we typically do. Okay, so that means the width of this rectangle is delta x. I now need the length of it, so I can do length times width to get area. Now to find the length of it, I'm going to think about this in terms of similar triangles. So again, I'm going to draw this picture one more time because my graphic is getting a little cluttered with values and lines and stuff like that. So here's the original triangle. It's 6 by 4. Right? And what I'm doing, imagine this dashed line right here as being this line right here. So what that means is that the height of this thing is that xi star right there. My goal is to figure out what this length is right here. But I can see that this triangle is similar to the larger one that it's living inside, because these angles would all be congruent to each other. That means I can set up proportions here. So let me temporarily call this side A, and I want to set up a proportion. So if I set the base over the height of my smaller triangle, A over xi star, and I set that equal to the base over the height of the larger triangle, so that's 6 over 4, or 3/2, I'm going to get A equals 3/2 xi star. I just realized that I was off the page there. Okay, sorry about that. So this is the work that I was just doing a second ago. That gives me the length of this line, which is the length of that rectangle right there. So that gives me the area of that rectangle. I'm going to call it AI because remember that this is one of a bunch of rectangles that I'm using to approximate my force. And I'm going to think of it as the ith rectangle because I'm using an I there. So AI is equal to the length times the width of that rectangle. Here's where we found the length, 3/2 xi star. Times delta x, that's the width of that rectangle, okay? Now, what do we want to do? Well, the next step is going to be to find the hydrostatic pressure acting on that rectangle. And if you notice, the units that are being used here are feet. So we're in imperial units, from US customary units. Whoops. So what we showed on the other page is that the pressure, PI, the hydrostatic pressure, is equal to our weight density, which is what this represents, times the distance. I'm going to call it DI, but the distance from that rectangle to the surface. Okay, so I need both of those quantities. Now on the previous page, we just stated that because we're dealing with water, we automatically know the weight density of water. It's 62.5 pounds per square foot. Now remember, this is not something that we derived. This is something that I'm just telling you is the case. We've verified that experimentally in the sciences, and we're just using that fact here, okay? But the distance, what is the distance from this rectangle here to the surface of the water? Well, I'm starting at a height of 7 and going down to xi star. So the difference between these values gives me that distance below the surface, 7 minus xi star. That's what the pressure, or the hydrostatic pressure acting on that little rectangle is. Now we want the force acting on that rectangle, Fi. Remember, force is equal to pressure times area, because pressure was divided to be force divided by area. So solving for force would be Pi times AI, both of which we've already found. So notice the sequence of steps here. Finding the area of your approximating rectangle, then finding the pressure acting on it, and then finding the force from those two things that we just did. So I need to multiply these two things together. This is equal to 62.5 times 7 minus xi star times 3/2 xi star delta x. I can simplify this a little bit. I can multiply these constants together and maybe even rearrange some things. 62.5 times 3/2 is 93.75. And then let's move the xi star here, just because that's typically where I would see it. And then 7 minus xi star. There, delta x. All right, so now what do we have? We have the hydrostatic force acting on our approximating rectangle here. But what we want is the hydrostatic force acting on the entire plate. If I were to sum this expression for all n, let's say that we divided our interval into n subintervals. If I were to do this approximation for all n of these approximating rectangles, then I would have an approximation for the hydrostatic force acting on the entire triangular plate. And as we keep seeing over and over and over again, this thing, which would give us a Riemann sum when we add it all up, is improved in its accuracy as we take the limit as those subintervals go to infinity, the number of those subintervals. So if I applied a limit as n, the number of subintervals goes to infinity, this thing is going to lead me to a definite integral, or rather the Riemann sum that I get from this would lead to a definite integral. So what does that definite integral look like? F, the hydrostatic force acting on the entire plate, is the definite integral from 0 to 4, because that's where all of these approximating rectangles are coming from, 0 to 4, of, here's where the integrand is going to come from. Remember, all of your xi stars become x's, so I get 93.75 x times 7 minus x. Then your delta x becomes a dx. And now we have an integral that's fairly straightforward to solve. So I'm going to get 93.75. I can bring that out of my integral. 0 to 4. Let's multiply the x into the parentheses. So I get 7x minus x squared dx. This becomes 93.75. It's a polynomial. Those are straightforward to integrate. So I get 7/2 x squared minus 1/3 x cubed from 0 to 4. I can see that plugging a 0 into this makes all of it go to 0. So really, I just need to worry about the 4. Plugging a 4 in here is going to end up giving me 3,250 And then I need to make sure, this is my answer, but I need to make sure I'm using the correct units. So again, we're in imperial units, feet. That's my clue that I'm looking at imperial or US customary units. That means that my force is measured in pounds. 3,250 pounds is the total force acting on that triangular plate, okay? Now, we're going to do another example in the next video where we do the same sort of thing, but with metric units and kind of a different shaped plate. But I want to point something out that's going to be a trend throughout this section and then a lot of the work that we do from here forward. In a lot of the definite integrals that I've evaluated in previous videos, I've gone through the steps of actually plugging the 4 and the 0 in, evaluating it using all the arithmetic, maybe, you know, ending that computation with a calculator or something. In a lot of the work that we're going to do here forward, I'm going to get us basically to this step, and then I'm going to go to the answer. And that's because we've done so many of the examples where we do all of the steps getting from here to here, but it's really just a whole bunch of arithmetic. It's stuff that you shouldn't need me to show you every single time. So I'm going to trust that you can do the work going from here to here. Now on a test or on your homework, I want to see the steps going from here to here. Maybe not every single intricate little step, you know, get it to the point where you have something that you could plug into a calculator at least. But just because I'm not showing the steps from here to here does not mean that you shouldn't be doing that. I'm doing it to save a little time and because we've already done all that work for tons of previous problems. Okay, so that's going to be the end of our first video for 8.3.